let's now look at some problems involving the derivative as a rate of change, but not ones that involve things like velocity and acceleration. So you can find the rate of change for any function. And so here's an example involving economics. So in economics, you have like cost, revenue, profit. So the cost is how much it costs you to make the products. The revenue is how much you make when you sell the products. The profit is the difference between your revenue minus your cost. And this example here, I have a revenue equation. And so the idea is this is how much you would make by selling X washing machines per week, I think, is the idea. So so this is like a weekly thing. This is, if you sold like 100 washing machines in a week, this is how much revenue you would make for doing that. So the idea of marginal revenue, or the same as like marginal cost or marginal profit, this is the rate of change. Marginal revenue is the rate of change of the revenue function, or the rate of change of the cost function, or the rate of change of the profit function. And so the rate of change is how much the in this case, how much the revenue would change with respect to the number of products, right? So kind of like 25 miles per hour. That tells you if you win another, at that rate, if you go another hour, you'd go 25 miles. So marginal revenue would be like a certain amount of money per product, meaning at that rate, if you sold one more product, that's the amount you would make for that particular rate. Okay, so the marginal revenue is that rate of change of the revenue. So this part A says find the marginal revenue when 100 machines are produced. So basically you're just taking the derivative of R of X. Okay, so I'm going to distribute that 20,000 over. I think that's going to be the easiest way to do this. And then I'm going to write this 1 over X as X to the negative 1. Okay, and now I'm going to find the derivative. So this will go away. The negative 1 comes down, making that positive, and then I subtract 1 from the exponent. So I get 20,000, and this should be 20,000 also, times X to the negative 2. So I could write this 20,000 over X squared. And so it wants to know the marginal cost when the revenue is, or when you sell 100 washing machines. What's the marginal cost? So now I'm just plugging in 100 into here. And when you do this, you actually get 20,000 divided by 10,000. I could do this in my head. That's equal to 2. Okay, so the idea here is your marginal revenue is $2. So at the rate that the revenue is changing at this point, if I sold one more washing machine, I would only make $2 extra. Okay, so there's a lot of factors. If you sell a whole bunch, there's supply and demand and saturation of the market and all this stuff. And so in this case, by selling one more washing machine, I'm not making a lot of extra money. Okay, so now it says use R of X to estimate how much the revenue will increase if sales increases from 100 to washing machines per week to 101 washing machines per week. So the idea here is at this rate, okay, if assuming that it stays at that rate, then if I sold one more washing machine, it would be, I would make $2. I would make $2 extra. Okay, so it's $2 for every one washing machine at that rate. Now, it won't be exactly $2 because this function, whatever it's doing, so this function actually looks like this, and it's kind of leveling out at 20,000 actually, to tell you the truth. So this thing's leveling out, and like at 100 it's here, right? And then what I just found was the derivative of at 100. So at 101 the derivative's a little less, and so over this interval the rate of change is changing from 100 to 101. So it's actually going to be, the true amount is going to be a little less than $2. Okay, so let's actually find the actual amount. And what I did here is, this is a graph of the function here, and I'm going to do second calc, and I'm going to find the value at 101, and it looks like the value, at 101. So what I just did is I found R at 101 is 19,801.98, and then the R value at 100. So now I'm going to plug in 100 here. So when I plug in 100, I get 19,800. And so basically, the actual amount, the difference between the two R values, so that would be like 101 minus R 100, is really $1.98. So like I said, a little bit less than $2. So in other words, the marginal rate is a very, very good approximation. Okay? And I should say it depends on how level this, if the derivative is really steep, it might not be that good of an approximation. But if it's very level, it is. I think that's the case. It depends on how fast things are changing. But usually we consider, if you're just considering one more, then the marginal cost is a very, very good estimate of how much you get for an increase in one. Okay. So then this wants us to find, finally, the last question here is, it says find the limit of r prime. So what you're really wanting to do, as x goes to infinity, you're wanting to find the limit of r prime, and that's this here. And if you notice, as x goes to infinity, a constant over something going to infinity just goes to 0. So it wants us to interpret this. So basically, as you sell more and more and more, your marginal revenue is going to 0. It's shrinking down to the point that you're really not making much more for one more washer machine. Okay, and so the marginal cost, you don't want to sell a whole bunch here, because your marginal cost, the increase in your revenue, is actually kind of going to 0, and so you want to find that amount in here somewhere where the difference is still big enough that it's worth, and that depends on how much your cost is and everything else, advertising or whatever. You figure out about how many you should sell per week. Okay, so that's like an economics example. And then I have one more here. So this is the stopping distance in feet for a car excuse me, traveling v miles per hour is given by this. So this seems like a speed, position, acceleration, or whatever, but the idea here is, what I'm putting in here is the velocity of the car in miles per hour, and I get out how many feet it takes for the car to stop. And so it's not the same as a position function, okay, even though it involves velocity, but velocity is the input, the output is how long it takes for the car to stop. So it wants us to find ds dv, and this is pretty easy. This is a quadratic, so I get 1.1, the v goes away, plus bring the 2 down, and I get 0.108 v. Okay, so it looked like that. And then it wants us to find the rate of change at v equals 35. So basically I'm just putting in 35 here. 1.1 plus 0.1. 35. Let me, oops. And so, this looks like 4.88 feet per, it would be like per mile per hour. This is the unit. So that's really kind of a weird thing. So if you increase by 1 mile per hour, this is like that marginal cost. At the rate that this function here, at the rate that this function is changing, if I increase if I increase at 35 miles per hour, if I increase to like 36 miles per hour, then my stopping distance is going to increase like by about 5 feet. That's the idea. This is asking for an interpretation. Kind of like marginal cost. It's 4.88 feet per mile per hour that you change. Okay? So it's an interesting rate there. So, so let's, it wants ds dv at v equals 75. So 1.1 plus 0.108 times 75. And then here, this is like 9.2 feet miles per hour. So at 75, if you increase to 76 miles per hour, okay, then it looks like your distance is going to change around 10 feet. So around 5 feet for 35 miles per hour, around 10 feet for 75 miles per hour. Okay, so that's the idea of doing these rates of change for something other than a position function. And so your rate of change is not necessarily velocity and acceleration, but has a different sort of meaning depending on the function.